Hello again, everyone. So we're going to wrap up topic 2 about energy flow here. So question 2C says chemical energy in carbon compounds flows through food chains by means of feeding. So when they say chemical energy in carbon compounds, what they're really talking about, this energy here, those are high energy electrons. Again, that's why we're talking about electrons. So you could also see this as saying high energy electrons in carbon compounds flow through the food chain by means of feeding. This is why we eat. We eat for high energy electrons. We then take the energy out of those electrons and convert that energy into chemical energy, which would be in the form of ATP. So living organisms cannot convert heat to other forms of energy, so heat is lost from ecosystems, tremendous amounts of heat. Then it says energy loss between trophic levels restricts the length of food chains and thus restricts the biomass of higher trophic levels. There's a reason why you see fewer apex predators. You might see, well, the classic example is where Palomar and Hilltop cross, right? You've got those stoplights there, and there's always all of these pigeons all over those stoplights. I see them all the time, right? Why do you see that many pigeons, but you only see 1 or 2 hawks? Okay, well, there's a reason why. The hawk is higher in the energy pyramid, thus it has access to less energy, less biomass. So what I need you to do on 2C is I need you to create a food chain. In fact, let's create a couple of them. Whatever you want to use as your organisms are fine. Please use real organisms. You know, let's not do unicorns. Unicorns are cool, but let's actually apply this. So on 2C, create a food chain. Create a terrestrial food chain, right? On the land. So whether that goes, I'll just make one up for Chula Vista here. Let's say grass, and grass is then grass captures energy and makes macromolecules. Those macromolecules are then consumed by a grasshopper. The macromolecules of the grasshopper would then be, let's say is consumed by the frog. And then the frog would be, let's say a snake, right? And then the snake would be consumed, let's say, by a bird, right? So notice the direction of my arrows here, all right? Those arrows show energy flow. Okay, so direction shows energy flow. Okay, the energy flows into the grass, right? So here's your sun, right? Gotta get a smiley face in the sun, come on. So the energy from the sun flows into the grass, right? In the form of sunlight. Excite the electrons in photosynthesis, and then the energy flows through the ecosystem all the way up to the bird. So create a terrestrial ecosystem, whether you want that to be in Chula Vista, up in Washington State and Oregon, whether you make that in the tropical rainforest, whether you make it up into the Arctic, whatever you want, okay? Then let's do an aquatic food chain. Something in the water. Now, if this is, again, in the Arctic Circle, up where it's really cold, you want to go saltwater, you want to go freshwater, whatever you want, okay? And then what we need to be sure to address, and same thing on this aquatic food chain, show the sequence of the organisms. Make it a minimum of 4, hopefully 5. Really look up real examples, okay? And what I want you to address is why. Why are there fewer organisms as you go up the food chain? Okay, this is really important. Why are there billions of plants, but then there's only millions of ants, and then maybe tens of thousands of pigeons, but there's only like 30 hawks in an ecosystem? Why? Right? It's all about energy loss. the transfer of energy is actually very inefficient. Only 10% of the energy is transferred from each level. It's 90% loss to heat loss and inefficient digestion. So, energy loss due to heat and inefficient digestion. We do not digest all of the macromolecules we eat. Classic example, the cellulose husk, that yellow husk on corn. That's why we joke and say corn in, corn out. Okay, so that's 2C. Be creative here. Make a terrestrial food chain and an aquatic food chain. And then be sure to address why there's fewer organisms at the top. All right, so that takes care of 2C. So now we want to take a look at 2D. So 2D says create a quantitative, we need numbers here. Don't forget there's two kinds of data, qualitative and quantitative. So qualitative qualities like bigger, faster, slower, green, yellow, blue. That's qualitative data, okay? Whereas when you're talking about quantitative data, that's a specific value. That's a quantity. It's a number. So create a number-based energy pyramid that is drawn to scale. That's important. IB loves to ask this question on paper 2 as a short answer diagram question. They really like it. So draw a quantitative energy pyramid that is drawn to scale and is stepped, not triangular. Notice the not. The triangular energy pyramid is middle school stuff. That's little kid stuff. We're big kids now. So discuss how biomass in terrestrial ecosystems diminishes in energy loss. That's the same thing they ask us to address here. When IB mentions things multiple times, they're telling you that they think it's important. So you need to be sure to address why there's less biomass at the top than at the bottom of any food chain or food web. So again, quantitative. Whenever you hear quantitative, numbers. Okay? Well, except for ratios, all numbers in science have units. Numbers without units are meaningless unless, of course, it's a ratio. So what are we talking about here? We're talking about energy. And the units for energy are joules. Chemists and physicists love to name their units after dead chemists and dead physicists. So there was a physicist named Joule, his last name, and so in honor of the work that he did in physics, late 1800s, early 1900s, they named the energy of unit after him. And how we actually do this is it's kilojoules or thousands of joules per second. That's the energy unit for food webs and food chains. Now, when you refer to, let's see if I can spell environment. Environment, there we go. When you talk about environments, you're talking about the sun. You're talking about the sun putting energy into the ecosystem. And there, we call it kilojoules per second. Excuse me. Kilojoules per meter squared per second. Okay? So you will also see that as kilojoules per meter squared second to the -1. All right, so it's how much energy is put in every square meter per second, okay? This is the same quantity that they talk about when you get into solar panels. How much energy can the panel absorb per square meter per unit time, right? So they asked for a stepped energy pyramid, okay? So get yourself a ruler. If you don't happen to have one, then you will approximate. And you're going to create a stepped energy pyramid that has 4 steps to it. So I'm going to need the width of my ruler here. 1, 2, 3, and 4. So I did the width of my ruler 4 times, okay? And why? Because the base of my pyramid is going to be 10 centimeters long. So there's 5, there's 10. Okay, and then I come down here, and let's let's see, let's line it up about like that. Hopefully that's close to the middle. And there's 5, and there's 10. There we go. Okay, so make this 10 centimeters. Now, if you don't have a ruler, all right, the width of your pinky is right about 1 centimeter. From here to here is about 1 centimeter. So if you don't have a ruler, draw a box that's 10 pinkies wide, okay? So 10 centimeters, fine. Well, then we had talked about how only 10% of the energy is transferred. Well, if only 10% of the energy is transferred, 1/10 of that would only be 1 centimeter. There is 1/10, 1 centimeter. And same thing, if you don't have a ruler, notice, that's the width of your pinky. Okay, so what we're trying to show here is while there's 10 centimeters of energy here, you only transfer 10% of that. You have a 90% loss. Okay, well then, and also notice how the depth of each step is the same. The depth doesn't get smaller. The depth is all the same. Well, if that's 1 centimeter, then 1/10 of that is 1 millimeter, which is, I'm going to come down just a little bit here, which is that. And I'm going to have to use the ruler. I can draw pretty straight lines, but not that straight. Boom. So now that is only 1 millimeter, or again, 1/10 of the previous step. And then now, just get as thin as you can. That's not really 1/10, but go with me on that. So supposedly, this is 0.1 millimeters, but of course the tip of the pen is wider, right? So this is your stepped energy pyramid, right? So what you have here then is here are your producers, like your grass. Here's your primary consumer. What we talked about earlier was probably a grasshopper or some other insect. Then a secondary consumer, something like a frog, right? And then a tertiary consumer. So look at how quickly this energy decreases. It's dramatic, okay? Then come over here and pick a number here. We know that our units are kilojoules per meter squared per second. Kilojoules per meter squared per second. Hey, kilojoules per meter second, per meter second. There we go. And then of course, kilojoules per meter squared per second. There's our units. Pick values here. Pick any value you want. Choose a value, okay? So I would make this number 6 digits long, okay? So I'm going to pick 100,000. So if there's 100,000 kilojoules per meter squared per second, this is how much energy the sun dumps into the ecosystem, and it's captured by the producers, okay? All right, but if only 10% of this is transferred, 10% of 100,000, of in math means times, so 0.1 times 100,000 is only 10,000 kilojoules. Only 10,000 of the original 100,000 are available to the frogs. No, excuse me, to the grasshoppers. And then only 10% of that, only 1,000 kilojoules of the original 100,000 are available. Let's see, it was grasshoppers, frogs, okay? And then 10% of that, only 100 kilojoules of the original 100,000 kilojoules are available to your tertiary consumer. So this is why your population at the top is small. You have a smaller population here. You have less biomass. Why? It's obvious. You have a smaller population, you have less biomass because they have access to less energy. There's a reason why there's few lions, there's few polar bears, there's few hawks or eagles, all right? They're vulnerable because by being at the top, while they may not have to worry about predation, they don't have access to as much energy as the individuals down here. Now, the individuals down here, good news, right? You have access to a lot more energy, much larger population. What's the bad news? You're prey for a lot of other organisms. So it's a choice. There's always good news and bad news. Okay, so again, discuss how your biomass diminishes, your biomass decreases with the energy loss. There's smaller and smaller populations as you go up the food chain or up the food web because there's less energy available. You know, you'll hear people say, oh, there's fewer hawks because they can't handle it. It has nothing to do with the animal's choice. It's what the animal has access to. All right, and then tie this energy pyramid back to your food chains that you made with the aquatic and the terrestrial ecosystems. So that's 2C and 2D, and that should wrap up topic 2.